dude?
I'm here if you can hear me.
Yes. Oh, that is so cool. So some people may know you from your newsletter that goes out to 50,000 people, right? Some people may know you from the work at Lightning AI that you're doing. Others may just follow you on LinkedIn, and you've been in the game for 10 years now. It is so cool to see what you're working on and how you share it with all of us. And I love your talks, and I'm so thankful that you've come to give us a talk here. I am going to put you on the spot, though, real quick, because you don't accept my LinkedIn request. What's up, dude?
Didn't I? Oh, I lost total control over, I think my LinkedIn feed. Maybe there will be, or I hope there will be an AI for that in the future.
There we go.
But I need to double check that one then.
All right. I hope so. I hope that that happens. Now, I am super excited because you've got a conversation for us about fine-tuning. And anyone that has been trying to put LLMs into production for the last, 6 months has probably gone through some way of fine-tuning. And so this is very, very topical. I'm going to hand it over to you. I think you've got some slides that you're going to share, and we're going to get rocking, man. Feel free. I'll be back in 20 minutes, and anyone who has questions, throw them in Slido. I'll be asking them to Sebastian. All right? It's all you.
Yeah. Thank you for the kind introduction. And I can see, you can see my slides, so I think I can get going here. In my talk, I want to talk a bit about fine-tuning open source large language models. And so this is an MLOps conference, but this will be not about the deployment. This will be essentially the steps prior to deployment, how to fine-tune open source large language models for certain tasks. So there was already a kind introduction, but about me briefly, I am an AI researcher and educator at Lightning AI now. Previously, I was in academia where I was working on deep learning research, mostly focused on deep learning for ordinal regression and computer vision. But in recent years, I would say I shifted more towards large language models. It's an exciting topic. So I wanted to briefly talk about using pre-trained large language models first, just to get everyone onto the same page in terms of how we use pre-trained large language models. And of course, the everyday typical use case is that we prompt something like ChatGPT to give us some explanations about topics we care about. And what's actually quite interesting and nice is that we can be pretty, I would say, precise. We can say, summarize something in, let's say, 2 sentences, and it will most of the time do this job pretty accurately. Just this morning, I tried out the new ChatGPT Vision interface. So here I just posted a LaTeX equation and asked it to extract the LaTeX code, which is also something that is super useful when I write papers or articles where I have an older article. I just, or I see something, I just see, okay, I want this LaTeX code, so I don't have to completely rewrite this from scratch. I can just make a screenshot, upload this, and it will do a quite good job for me for that. Of course, I should mention there are also other tools for that, like MathPix, which I'm using usually, but I was just trying this out with a simple example, and it works. So this would be one way we interact with large language models. There's a technique called prompting where this was more like, I would say, initially when large language models were developed, but it's also still relevant, where we want to sometimes ask the model multiple times. So for example, if we have a translation problem where here I want to, let's say, translate this language joke, I can then ask the language model in multiple ways. So here are just 3 different ways I can formulate my input prompt. And depending on the LLM you use, especially, let's say, with a smaller open source large language models, you might get different results. And some of these prompts work better than others. And if you follow the news, there's also this concept of chain of thought prompting, for example. I won't go too much into detail here, but the essence is essentially the way we format our input prompt currently can sometimes really make a big difference in terms of the results. Maybe in the future, we will see that this will go away, where when we develop even more capable large language models, that this becomes kind of redundant. But for now, that is something to keep in mind. Another way we use pre-trained large language models, it's a technique called retrieval augmented generation, where we essentially develop a hybrid system, a hybrid between a total LLM application, but also using, let's say, existing knowledge from documents. So for example, imagine you are a company and you have let's say, a documentation for your software, or you are developing an application. There is a big, let's say, knowledge base that you have. You could technically use an LLM or another embedding system to chunk up this document, create embeddings, and put that, for example, into a vector database. And then if you query an LLM with a prompt, you create an embedding and you can search for the most similar embeddings in that database then. And when you have the LLM generate the response, it would combine both your query, write its own response, but then also incorporate some of these embeddings from the database. And this is a very useful approach if you are developing a system where you already have a knowledge base and you want to return specific examples, let's say from a user documentation. So here it doesn't make sense for the LLM to really regenerate it if the answer is already in some documentation. But again, this is another use case. It's not the focus of this talk. The focus of this talk is on fine-tuning, where we take a pre-trained large language model and then fine-tune it on custom target tasks. So first, I wanted to briefly talk about building LLM classifiers. And the reason is, I believe that most real-world applications involve some sort of classification. So when we're developing applications, for example, email spam filters, detecting fake news, or even Twitter uses that for detecting toxic content and so forth, there are a lot of classification tasks that we encounter in practice where we want a model to classify something into categories. So for that, we can also fine-tune a large language model. So there are different approaches for doing that. One would be similar to what I talked about with the embedding. It's like what I call the feature-based approach, where we take a data set, we take a pre-trained transformer or LLM, and then we extract these embeddings and train a classifier on top of it. So the classifier here, that would be anything you like, support vector machine, logistic regression, something simple usually. And this does usually a okay job in terms of being a good classifier. Going one step further, there is this approach that I call usually fine-tuning 1, where it's relatively similar to the approach on the left, except that we insert one or more hidden layers and then have an output layer that we fine-tune. So we keep here, so the key also is that we keep the transformer frozen. We are just extracting the embeddings here, and we are just working with these output layers, and we can then fine-tune these output layers. And the idea is that the embeddings contain useful information that the last layers then can use to become a good classifier. Going even one step further, there is something I call usually fine-tuning 2, where we update all layers. So instead of just updating the output layers, we would update the whole transformer or the whole large language model, which can give us even better performance in certain cases. But it is also, of course, involving more updates and involving updating more parameters. So this is also more expensive usually. So when I was plotting this here as a rule of thumb, usually this feature-based approach is the cheapest, and the fine-tuning 2 approach, updating all layers, is the most expensive one. But then also you have a trade-off in terms of training efficiency. Feature-based is usually much cheaper than this other one. So it's really depends on the application. It's really something to try out. And sometimes there's also something in between fine-tuning 1 and 2 where you can get, let's say, most of the performance already by updating only a few layers in between. So when I benchmarked this on a simple data set, 50,000 examples of movie reviews where there were positive and negative movie reviews, whether someone liked the movie or not, I got 90% accuracy in like 3 minutes, 93% when I was updating the whole model. And that was for a small model. That was the Stillbird. I think it's about 60 million parameters. So it's not even a large language model, really. It's a small large language model. And I just want to show that large language models are also capable of these tasks in addition to generating texts. And also here for reference, when I was trying to fine-tune or to classify these examples with a logistic regression classifier or recurrent neural network, I never got above 90%. So I was always about 85%. So in that case, it's worthwhile to consider large language models also for these let's say, simpler classification use cases. But yeah, if you're interested, the code is, the link is at the bottom, so I won't go into much more detail about that. what I wanted to talk about now is I wanted to talk a bit about instruction fine-tuning. So this previous slide was a bit out of order. I wanted to talk about instruction fine-tuning, which is a different type of fine-tuning. It's not for classification, it's for LLMs to perform certain instructions or to answer with certain responses given an instruction. So here, an instruction could be, for example, write a limerick about a pelican, and the output is then what we want the LLM to generate. And this is the data set that we would have to collect, where you can think of it as a labeled data set. In contrast, in pre-training, we usually use unlabeled text, where it's just predicting the next word. Here, the LLM has to predict the next word in the output specifically. And there's also an optional input. So, for example, you can have an input field where you have an instruction like identify the odd one from the group. And then you have different inputs like carrot, apple, banana, and grape. And then the LLM is supposed to answer with carrot. And you can also think of this as a type of classification task in a sense. But this is more general. This is like this instruction fine-tuning paradigm. And here I wanted to show you that this instruction fine-tuning is actually quite worthwhile if you compare it to a base model. So at the bottom, there is a GPT-3 base model, which is just a pre-trained model. And then above that, we have GPT-3 plus prompting, where this goes back to the beginning of the talk, where I showed you that we can format our input in different ways. And then if we add supervised fine-tuning to it, we get even better performance on the y-axis here. So this is an older paper using GPT-3, but of course, this also generalizes still to the newer LLMs as well. So fine-tuning is usually worthwhile, and most of the models you find on leaderboards on the top, they are usually fine-tuned in a supervised fashion. So fine-tuning can be expensive. So when you think back of the slides that I just showed about the classifier, updating all the layers is quite expensive. So there are, of course, methods that only update the last layers, but what we really want is we want to update the whole model, but in a parameter-efficient way. So for that, researchers develop parameter-efficient fine-tuning techniques, and there are really literally dozens of techniques out there. But if I had to pick one specific technique, then that would be low-rank adaptation, LoRA, which is currently the most popular one. So low-rank adaptation, in a nutshell, is a method for factorizing the weight update matrix. So if you have a task where you're fine-tuning a model, you have on the left-hand side the pre-trained weights. Let's say you're updating GPT model. Then usually if you fine-tune all the layers, you have this gradient descent process where you learn the update rule, like the updated weights. So how much you want to nudge the weights in a direction that minimizes the loss. And if you represent this as a separate matrix here, as the weight update matrix, this weight update matrix with the delta weights, the changes, have the same size as the original weights. And in LoRA, we factorize this large matrix into two smaller matrices. And this would be essentially a low-rank approximation. And so here I'm showing you this figure for one particular weight matrix. But of course, in a large language model, there are lots of these weight matrices. So we have the Q, K, and V matrices, and we have also multiple layers. We have the multi-head attention blocks, and we also have the output layers, the multi-layer perceptron layers at the end, and so forth. So there are lots of places where we can do this factorization. And just to give you an example with numbers, so on the left-hand side, if this matrix is 5,000 by 1,000 weights, then we have 5 million parameters. Whereas when we factorize this, for example, into two matrices, like 5,000 times 10 and 10 times 1,000, then we end up with only 60,000 parameters in total. So for this particular matrix, so you can save a lot of, let's say parameters by just using this low-rank approximation approach. And according to research for specific tasks, this approaches the same performance as the whole weight update, but of course not in a general sense, only for specific tasks that you fine-tune this on. But it is definitely something worthwhile to consider because it saves you a lot of computation time compared to updating all the weights. So I was doing some speed tests here. So I was comparing this full fine-tuning, updating all the weights compared to, for example, LoRA and some of the other parameter-efficient fine-tuning techniques. And as you can see here, the full fine-tuning took about 9 hours on 6 GPUs. So that was using deep speed with CPU offloading. So that took additional time, and that was necessary because even on 6 GPUs, I couldn't fit the full model, the 7 billion model, onto full 6 GPUs, even if I distributed it. Whereas with LoRa, I could fit that on 1 GPU and train that in about 1 hour. So just for comparison. And this was for 50,000 training examples in Alpaca. And memory-wise, for the full fine-tuning, I used the full memory for all the GPUs. Whereas for LoRa or the other methods, it was about 16 gigabytes. And this is the regular LoRa. When I was using quantized LoRa, that went even down to like 13, 12 gigabytes. So quantized LoRa takes a bit more computation time because there's an additional quantization step, but you can even bring that further down. So just to illustrate, parameter-efficient fine-tuning is a technique that makes it possible to really train relatively large language models on a single GPU, making it more accessible than also for deployment scenarios. So to give you a concrete example and application, I wanted to talk a bit about an open source library that I'm helping to develop, where I'm a contributor. And so this is fully open source. We developed this at Lightning, but it is available to everyone, no restrictions, on a Apache license. So that's something you can also use in deployment scenarios. So I wanted to briefly show you how it works and how you can use it. And of course, there is more information on the GitHub repository here at the bottom. So here it's just an overview that there are a lot of documentation documents that we wrote. So in case you want more specific, let's say, guidance, you can find a lot of information there. I will only go over the very basics in the last 2 to 3 minutes. So if you're interested in fine-tuning LLMs, and you are interested in using, let's say, cutting-edge, state-of-the-art LLMs like Falcon, Mistral, Llama 2, and so forth. So for this repository, you would, so I also should say maybe why this repository and not, let's say, some other repositories. What I like about it is essentially that it is easy and hackable. So what it is essentially scripts that you can look at and modify, and you have a lot of options there. Of course, it's not all encapsulated where it takes away all the options, which is nice for some people, but it allows you to modify things and play around with that. So here I'm showing you the very basics. So if you want to set it up, you would clone the repository, install the requirements. And the second step would be then downloading a model. And as I mentioned, most of the current models are available. And if there's a model that you would like to use and it's not available, it's usually not a big deal to add it. So there would be Llama 2, Falcon, Longchat, StableLM, CodeLlama, Mistral, Phi 1.5, which is a nice 1.5 billion parameter model, for example. So you would download the model, just one command, Python download the name of the model, convert the checkpoint into the format that is supported by LitGPT. It's really just like 2 lines of code. Then preparing a data set. So over the last couple of weeks, we also added a lot of data sets. And there's also a way you can load a data set from a custom CSV file, for example. So these are just available. And these are some data sets that I'm currently also using in some other projects. For example, there's currently the NeRS efficiency challenge, which is quite interesting. So you prepare a data set. And why is that necessary? Why do we have to prepare a data set specific for a model? So here I'm using the Mistral model, which is really the most popular model since of last week, because it's pretty good for a 7 billion parameter model. The reason is that each model has a different tokenizer. So not all of them have different tokenizers, but it's really most of them may have different tokenizers. So you have to prepare a data set specifically for an LLM to make sure you use the same tokenizer that the researchers used for pre-training that large language model. So you prepare the data set, and then really you can already get going with the fine-tuning. It's really just one code snippet here, where you, for example, use LoRa fine-tuning with a checkpoint, the pre-trained model. Here I'm using 2 settings, a precision BF16 true, which means brain float 16, so to save you some compute memory and to make it faster. That is usually what most people use. If your GPU doesn't support it, you can also use a regular 16-bit precision. And then I'm quantizing it here with a normal float 4, which would be QLoRa essentially, which is even more memory efficient. And then, it should train about, it would be about 1 hour here or 2 hours. I think it's like a slower GPU I used here. It would be, I think, a A10, which is quite cheap. So you can train it on a small, cheap, relatively cheap GPU. And yeah, if you're interested, also there is this NERS large language model efficiency challenge, which is about training one LLM for one GPU for one day. And I'm just mentioning that because if you care about LLM deployment, there may be a lot of cool LLMs coming out of this challenge because people really work on making LLM training more efficient. So developing the best LLM in a given compute and time budget. And this LitGPT repository I just mentioned, this happened to be selected originally as the official starter kit. So it's still the official starter kit, and people use it to compete in this competition. But of course, you can use any framework. But LitGPT is, I think, the favorite here because it's so easy to use and pretty customizable and so forth. So I was just doing some playing around here on the weekend where I did some submissions, which ended up being first on the leaderboard, but it's not first anymore. So some people were already coming up with better solutions. It's pretty interesting to kind of keep track of that. And with that, I think I'm also already out of time. It was quite the whirlwind tour here, highlighting different fine-tuning techniques. But if you have any questions, I think we have 5 minutes for questions.
Oh, dude, there's questions.
Chat more.
Yeah,
there's questions.
There's a lot of questions coming through. People are really stoked at what you're doing. So I'm going to fire off a few of them for you. First one's about how do you see the performance trade-off between using techniques like LoRa and full fine-tuning for complex tasks demanding reasoning abilities? Can we use Lightning AI for full fine-tuning? What are the advantages compared to other libraries?
That's a very good question so the first question was about LoRa and the trade-off. Yeah. If you look at the original research paper, I don't have the figure here, but they showed that with LoRa, you can get the same performance as full GPT fine-tuning, as a full fine-tuning. And also you can do full fine-tuning in LitGPT. So I have this, I specifically added this script for full fine-tuning. The performance trade-off is, you get better computation performance, but you may not. So if you fine-tune something with LoRa, you usually have a goal in mind. If you take a general model, so you assume this model is good on general tasks, you assume that, so for the fine-tuning, you do a low-rank approximation that you have for a specific task, a low-rank situation where you only update the weights for certain targets or target tasks. So you may, so technically you may preserve the original performance on the original tasks, but in practice, I noticed you get worse performance on tasks that you don't fine-tune it on or for. But this is kind of like, I would say, by design, where if you already have a pretty capable model that is a generalist model, then there would be no need to fine-tune it with LoRa, in my opinion. So you could just use it as is if it's already very capable in general tasks. So in my opinion, LoRa is really to make it better on certain tasks you care about in a certain application scenario. So if that answers the question. And also, one important thing is LoRa has a lot of hyperparameters. So if I go back here, if you look at this R here, that's like the hyperparameter for the width of these matrices here. That is also a big factor in terms of how well it works. It's also a trade-off. The more parameters you allow here, the better it may be. And also, you have to consider there are multiple layers in the network. So there's also hyperparameter. So do you want to fine-tune the output layers only, or all the layers and so forth? And you can change that also in LitGPT. So if you go to the script, there are all the settings for which layers to update and so forth. So you have to also kind of like, depending on what you try to do, you can try different hyperparameter settings too. So yeah, if that answers it, yeah.
More than enough, dude. Awesome. Next one up is about when you would consider full layer fine-tuning and how effective it is for text classification tasks. So I honestly, I must say I removed a lot of slides because otherwise it would be a 50-minute talk and not a 20-minute talk. But so for the full fine-tuning, if you go to this repository, I think I have a figure in there. If not, I will. I have it somewhere. I will share it. And so the full fine tuning here, it takes much more resources. It's much slower, but you can get better performance. But I noticed so what I did is I did an experiment starting out with the output layer and then adding one more layer at a time or one more transformer block at a time. And I would say like 2 or 3 transformer blocks in,
the performance already saturated. So I think this model had like 6 or 7 transformer blocks, or maybe it was 12. But you didn't have to fine-tune all of them. If you fine-tuned the first couple of them, you already kind of saturated the performance. So in that sense, it's maybe not necessary to do the full fine-tuning. You can really just get away with fine-tuning a few of the first transformer blocks from counting from the output layer. And yeah, but this, I guess, depends a bit on the data set, but I would say it's worth trying just to start out with the output layer and then working your way towards full fine-tuning and see if you can save some time by just, doing the output layers.
Well, speaking of full fine-tuning and kind of pulling a little bit more on that thread, do you still recommend the full fine-tuning, do you still recommend the fine-tuning to updates to all layers for instruction fine-tuning, or does it have some sort of trade-off?
I think it's worthwhile. It's a good baseline if you have a lot of resources. But yeah, like I showed here, where was it? It is pretty infeasible if you don't have the resources. It's very expensive. If you consider, usually, I think A100s, if you have 8 of them, it costs like $30, $40 an hour. If you fine tune for 10 hours, it's like it's $400 for one experiment, right? So I think it's worthwhile if you have the resources. If you don't have any budget or limitation, well, I would say full fine tuning. But otherwise, with LoRa and so forth, you can get pretty good approximations. And depending on the target task, you may actually get better bang for the buck. So you can also. So here I'm showing you full fine-tuning for a 7 billion parameter model. If you have the resources, instead of all throwing them onto full fine-tuning for that 7 billion model, you may just want to use LoRa on a 10 times bigger model, for example, right? So it would be also something to consider.
So I'm going to give you a real easy one now, because keep in mind, the next speaker is the CTO of Mistral himself, Timothy.
Oh.
So this question here is, which LLM do you usually use for fine-tuning? Does this vary based on the use case?
Yeah, so right now, actually, I did not know that we have the CTO of Mistral here, but yeah, we just added Mistral support to LitGPT yesterday.
Nice.
So that is right now something I'm playing around with. And also for the NERS challenge, it might be an interesting candidate. So for the NERS challenge, I would not use the instruct version, because the goal is really to start with a base model and then come up with the own instruct version. But yeah, so that is currently my hottest candidate too, because it's, I guess, fresh, interesting, and works, or seems to work well.
Yes, I know a lot of people love it, and I'm excited for his talk. Dude, this has been awesome. As everyone can see, fine-tuning is not as straightforward as you would think it is. I made a shirt design just for you and this talk, and I think we can pull it up. It's on my screen right now. Let's see. Can you see this?
Oh, wow.
He's speechless. There he is. There it is. That's just for you. I don't know if you can read it. It's just as easy as fine-tuning, right, Sebastian? If people listen to your talk, hopefully it is as easy as fine-tuning. Now, man, this was awesome. If anyone wants to continue the conversation with you, as I mentioned before, you've got a newsletter. You're very, very active on social. You're sharing a lot of incredible information with us all, and we appreciate that so much. I'm floored that you said yes to coming on here and giving this talk, and so I want to thank you. And now we got to keep it moving.